Yasin is going to talk about fair machine learning with uncertain group identities. Cyrus is a visiting assistant professor at Brown University, where he also recently completed his doctoral studies. A perennial scholar of probability, Cyrus has worked in many areas, ranging from statistical significant questions in data science and machine learning to econometrics and social justice, where he raises and attempts to answer fundamental questions of what it means to share, allocate, and learn fairly. His signature is the application of techniques from statistical learning theory to study how quickly and under what condition various quantity of interest can be estimated from data. He also works in the analysis of randomized algorithms, Markov chain Monte Carlo, and statistical data science and empirical game theory. So Cyrus, the floor is yours.
Thank you, Christina. Can everyone hear me and see my slides?
Yes, we do.
Wonderful. So as mentioned, I will be talking about fair machine learning methods when we don't have full information about the group identity of the instances that we're learning from. I want to briefly lead by talking a little bit about fairness in machine learning in general. We now understand that in practice, machine learning systems are often trained on one group and then applied to a broader, more diverse community of people. And this can lead to differential performance across different groups, which can lead directly to algorithmic discrimination. The most famous example is probably in facial recognition, where we know that these systems are quite accurate on light-skinned males, but are less accurate on dark-skinned people and females, and in particular, darker-skinned females. This leads directly to algorithmic discrimination because these facial recognition systems can be used in policing and other systems where being misclassified can be extremely harmful to somebody. So I want to know, when I see something like this, what has actually caused this problem to happen? Is it inherently an issue with machine learning in general? Is it a problem with the data from which a machine is learning? Or is it a problem with how we are training these facial recognition systems? In order to answer this question, we need to talk a little bit about what race actually means. We need to understand that race and other protected groups are both continuously evolving social constructs and inextricably woven into the fabric of society. It may seem like we can solve this contradiction by just saying that computers are neutral, so employing computers to solve these problems should fix issues of discrimination. However, this perspective is extremely naive. While it is true that a computer itself doesn't have any sort of racial discrimination built into its physical structure, the data that we feed these systems may not be neutral. Selection bias exists on the part of the people who are training these systems and actually choosing which ones to deploy and which ones not to deploy. This attitude of race blindness solving all of our problems is often just a mask for racism, where people like the status quo and make this claim so they don't need to address difficult issues. And finally, the objectives that we feed into our machine learning systems encode our preferences in ways that can lead to discrimination. In other words, we need to understand race and understand discrimination in order to effectively combat it. Now, in this context, we have to have a notion of a protected group. And these are two separate problems. The first one is to select which groups should be protected, and the second one is to treat these protected groups fairly. Both are arguably data problems, but problem two is clearly algorithmic, and that's what we're going to focus on this talk. For our purposes, we will assume that we have meaningful protected groups, and we want to treat them fairly, and these groups can be on the basis of race, gender, sexuality, or other criteria. In practice, the real world is more complicated, but we're going to assume discrete groups for our purposes today. One of the most famous data sets in machine learning, in particular fair machine learning, is the adult data set. This is a standard benchmark, and it contains information on the race, sex, age, income, other attributes of each individual. Now, race is broken down into groups white, Asian Pacific Islander, American Indian Eskimo, other, and black. This is an extremely coarse classification, and we could examine subgroups within each of these categories that face different discrimination and stereotypes, They have different opportunities and material circumstances. And in order to do anything with that, we would need fine-grained group information, but rarely is this actually available. For example, the population of Earth is 8 billion people approximately, and the population of Asia is 4.5 billion. Yet, Asian Pacific Islander was just a single category out of only 5. This seems like a problem. We could split into more fine-grained subgroups, and doing so is a highly political decision. But in order to do that, it seems like we're going to need more information on the individuals in this and other data sets. The question I ask is, can we perform group-centric fair machine learning if we are not given group labels? In particular, is partial information on these group labels sufficient to learn? What is partial information and where can we find it? In order to answer these questions, we need to dive into what machine learning is. Machine learning is a lot of different things to different people, but for our purposes, we're going to assume we're learning some function h from a hypothesis class curly h to optimize some objective. This is extremely general. It encompasses the idea of supervised learning, where we're predicting a label y given a features x. It encompasses common tasks like classification, regression, or conditional density estimation. And these have key applications like speech transcription, facial recognition, and medical diagnosis. So we can think of everything I talk about today as a metaphor for these sorts of tasks. Now, in learning linear classifiers is a simple example. We need to first say, how much data do we need? And we need to collect that data. Now, if we want to learn to classify between red and blue points with a linear classifier, we need to select the line that will minimize the number of mistakes, or the risk, which we find here, and it makes 0 mistakes. It will be impossible to do better than that. We also need to ask, what is the computational process by which I learn this line? In fact, this particular example is not computationally efficient in higher dimensions, but there are other algorithms that would handle higher dimensional spaces better. Now, nothing about that example has anything to do with fairness. When we bring fairness into the equation, we need more. In standard machine learning, we're trying to learn the hypothesis H star that minimizes the expectation of the loss. In other words, makes the smallest number of mistakes. In fair machine learning, we have different groups that we're learning from, so we can't just minimize a single number. We need to consider a distribution over instances from each individual group, which you can think of as drawing samples from populations of different protected groups. We then want to still minimize something that represents our error, but rather than just a single expectation, we want to minimize a function m of the expected loss or risks of each individual group. This concept is called malfair minimization, and the malfair function m encodes some societal ideal of fairness. We can contrast this idea with constraint-based fairness, where rather than simply doing a minimization, we impose some statistic, usually on these expectations, to ensure that we treat them fairly, but I will not be covering that topic in today's talk. This idea comes from, or is deeply rooted in econometrics, where minimizing malfair is analogous to maximizing welfare over the population, or some metric of overall well-being. And as always in machine learning, we don't actually know the distributions, and we will have to work from training samples. Now, what actually is a malfair function? Well, we have some metric of disutility or loss, which will measure a negative attribute for specific people, or overall when we average it for a group. Malfair then summarizes population level disutility. For example, the utilitarian malfair is simply the average loss across a group, or across all groups, sorry. And the egalitarian malfair would be the maximum loss across every group. So if I came up with a classifier that worked very well for all but one group, then the egalitarian malfair would still be large, because it would look at the loss of the worst performing group and say, that is how I'm going to measure this classifier. Because it is based on the worst performing group, the egalitarian malfair will incentivize aiding the most needy or highest risk group before all others. To illustrate this concept, we have three populations. In A, everyone is equally happy. In B, there's some amount of disparity, but on average, everyone is equally happy. And in C, everyone is happy except for one person who is really suffering. The utilitarian measurement of A and B is the same, and by the utilitarian standard, C would actually be the best society. But by the egalitarian metric, A is slightly better than B, because while there is the same total happiness, A is more even, and C is actually ranked very poorly because we've moved all of the suffering onto one individual person. Now, this concept of utilitarian welfare has a problem, which is that we can ignore the needy in favor of privileged groups, which may be easier to satisfy in some cases. And the egalitarian metric has another problem, which is that it can ignore large numbers of people in favor of a small minority group that is unhappy with the situation. So neither is perfect, but both are ways to look at the world and different ideals of fairness. Now, there's actually an infinite spectrum of viable choices, of which the utilitarian and egalitarian are both special cases. I'm going to introduce what's called the power mean. Suppose we have a vector of utility or loss values across a population. We're going to take the pth power of each entry, average those, and then take the pth root. There are some special cases for values of p for which that equation is not defined, but the first equation is the most important. When we do this on a population with 3 individuals with loss 1, 2, and 3, when we take p equals 1, this becomes a simple average, which has malfair 1. As we take p towards infinity, this function tends towards being the maximum, so we actually tend toward the egalitarian case. And the values between 1 and infinity put more emphasis on the higher risk groups than on the lower risk groups. So they're fair in the sense that they care more about the people who are suffering more, but not to the exclusion of everyone else. We can think of these functions as a smooth interpolation between the maximum, the arithmetic mean, or if we go in the other direction, also the minimum, the geometric mean, and the harmonic means. Now, when we're talking about machine learning, we've been given a malfair function m, and we've decided that is what our objective is to try to minimize this malfair, which quantifies overall suffering in our society. There would exist some optimal function h star that does minimize this objective, but we don't know it because we don't have all the information required to compute it. So we want to select or learn a hypothesis h hat. In particular, h hat should be almost as good as h star. For instance, if it were to be epsilon delta probably approximately correct, what we would want is, with probability at least 1 minus delta over all of the randomness in our sampling process by which we collected our data, we would want the malfair of the h hat function should be smaller than epsilon plus the malfair of the optimal h star function. In other words, you will learn something that is worse than the optimal thing, but not by more than the value epsilon. Now, examples that we could use for this would be if we were to take the utilitarian malfair, then this m function would just be a linear combination of expectations. So it would still be linear. It would just be a weighted risk minimization problem. In the egalitarian case, we would have what's called minimax fair learning. We want to minimize the maximum risk of any group. And in general, in the power mean case, we would have some nonlinear function that kind of compromises between the utilitarian and the egalitarian cases. Now, we talked about learning linear classifiers, but what happens when there are multiple groups of people that I want to classify? Well, I know I can handle each group individually. I want to separate the red suns from the blue suns, where the color is the class and the sun is the group, and I can do so and make no mistakes. Similarly, I can separate red moons from blue moons. But if I consider both the moon group and the sun group at the same time, there does not exist a line that will separate all the red points from all the blue points. I need to find a way to compromise. And I can do so by selecting the function h hat that minimizes the malfair of the risk values of the two groups. And that's this solid line here. and we can see it does make two mistakes, one on a blue sun and one on a red moon. So neither group is as happy as they would be without with their optimal with their first choice. But we do treat them fairly in the sense that we distribute the number of mistakes we make evenly across these groups. And we can choose a Malfair function that would affect how we make the trade-off between these multiple groups. Now, in fair machine learning, we, as always in machine learning, we get what is called overfitting. So our task, or what we've decided to do, was learn some h hat in our hypothesis class. And we have a loss function and a Malfair function by which we form our objective. And now the true Malfair would be the Malfair function of the expected loss with each group on the left. But the empirical Malfair would be an empirical estimate of this, which would be the Malfair of the empirical estimate of loss based on the samples that we've seen for each group on the right. Now, because in machine learning, we can only work with the samples we've been given, we don't actually have access to the distribution, it's impossible for us to compute the true Malfair of the function theta that we've learned. The best we can do is look at this empirical Malfair function. Now, in practice, the risk of a classifier, or the Malfair of a classifier, parameterized by theta, will not have the same empirical risk and, empirical Malfair and true Malfair. And the amount that they differ will also be a function of theta. So this blue line represents the empirical Malfair given a choice of theta. And in empirical Malfair minimization, what we do is we select the value of theta that minimizes this blue curve. Now, unfortunately, what we wanted was originally to minimize the red curve, which would be theta star. And theta hat and theta star are not actually the same. And this is kind of the central problem in machine learning, is how do we deal with the fact that we don't actually have these distributions, and what can we say based on only a sample? Now, this is an abstract example, but this is a practical example on real data that kind of illustrates the same thing. So we're back to the adult data set. And for each of the 5 groups, which are labeled black, gray, yellow, or orange, red, and blue, we have some value for their training error and some value for their test error. And if we look at a group like the blue other group, on the x-axis, we have the Malfair power. So when we take the Malfair equals 1, we're just throwing all the samples we have into the machine and treating them equally. And that results in better performance for some groups, like the white and Asian subgroups, than for other groups, like the black, the American Indian, and the other groups. But as we increase the Malfair power P, we're incentivized to make the situation better for the higher risk groups. And we see that this actually does happen in all 3 of the underprivileged groups. We see both their training and, well, we see that their training performances drop and become much closer to the performances of the white and the Asian groups. However, in some cases, we see their test performances actually get worse. And we always see the gap between their training and test performances grow. And this is because when we make a group more important to the function that we're optimizing, an inherent impact of that is we're going to try to overfit to the data we have because we're not actually looking at the distribution. So by increasing this Malfair power, we end up making things more fair to some of these subgroups, but at the same time, we also overfit more to them. So we have to quantify the amount that this happens and collect enough data so that this is not a significant problem in the accuracy of our final model. Now, the problem setting I've laid out, we're given the features X and the labels Y, but we're not given the protected group memberships. So for example, we're not given race values, or we're not given specific values for the race of individuals in the adults data set, but we might be given their sex, age, income, and other properties. Now, one idea that we could try would be to use imputation. It's a classic idea in machine learning where if we're given some data and it doesn't have all of the values we want, we can sometimes find a way to make something up for the values we don't have that's reasonably accurate. Usually we use this on missing feature values, estimate some X value given the remaining X values. And we can do this using unconditional or conditional averages or nearest neighbor methods, find similar training points and copy what their values that were missing for us, or other predictive methods. But this does create a problem when we're trying to apply it to learning missing group membership. This might be a bad idea because what we're essentially doing is we're learning to stereotype to estimate someone's race. If I don't tell you someone's race and tell you some other things and ask you to figure out their race, what you're doing is, by definition, you're kind of appealing to, possibly statistical stereotypes, but you're really trying to estimate what race someone is just based on these properties that you've seen. And moreover, if we do this, we don't get any theoretical guarantees for the accuracy of the process. So once we've done this, everything that we do downstream from here can be colored by the fact that we didn't actually use true race information. We instead estimated them, and if we estimated them incorrectly, we could end up with an unfair system, which is exactly what we were trying to avoid. So the idea in this work is to, instead of imputing every example individually, let's try to work with statistical constraints and actually get some rigorous guarantees on this method of working from partial information. Now, statistical constraints sound a little bit scary, so I created a fun graphic of a gumball machine to illustrate this idea. If I were to get one gumball from this machine and ask you to guess what color it was, you could not do so with any reasonable accuracy. However, if I get many gumballs from the machine, you can look at it and you can say, I can say there's roughly this many red, roughly this many yellow gumballs in the machine to begin with. So I can get a pretty good guess of how many of each color of gumball you got. In other words, some color assignments are feasible, like if there's approximately these numbers of each color of gumballs. But if I were to guess something like all 21 of these gumballs are red, you'd say that's very unlikely. So even though we can't say anything about individuals, we can say something about groups in aggregate. Now, the statistical constraints we generate are a little bit more complicated than this. We're given these labeled points, which are X values and Y values, but we're not given the group IDs or the Z values for each individual that we're trying to learn from. Now, partial information in our context will be a set, capital Z, such that the true labels are contained in that set. So it's a set of possible true labelings for the data I have. Now, usually we will say that each element in Z, rather than just being an individual group identity for each point, we can say it's a distribution over group identities for each point. And when we do that, we can say that the set Z is in the space of probability simplices for each item. In other words, sample one has some probability of being from group one, some probability of being from group two, and some probability of being from group three. Now, if you assign these probabilities to every sample in your data set, either that probability assignment will be feasible, in which case that assignment is in Z, or infeasible, in which case it is not in Z. And we're going to determine feasibility based on whether it makes sense with the statistics we know, like from the gumball machine. For a little bit more detail, we're going to create these statistics by measuring the overall population. And our statistics will measure the overall behavior of the unknown group labeling. Some Z will be unlikely or infeasible if it disagrees with these population statistics. And we will construct the feasible set Z based on group labelings that agree with many statistics. So although we can't know any individual's group labeling with certainty, it would be like trying to know a lot of information about a single molecule, we can say a lot about the aggregate behavior of all of our data, which is like trying to infer something about the overall behavior of a regular crystal of molecules. Now, we can visualize this idea of a feasible set where we start with this unconstrained set. And this would be all possible ways to label label the group of every training sample that I have. And somewhere in this unconstrained set, there is the unknown Z star, which is our true labeling. This doesn't tell us anything, because this is just anything that could be numerically possible. But once we impose a constraint, it tells us that some of these labelings are just statistically extremely unlikely to occur. So we're going to forget about them and just look at the labelings in this band. Now, that's one constraint, but we add additional constraints. And if we say all of these constraints need to be satisfied simultaneously for something to be considered feasible, the more constraints we have, the smaller their intersection becomes. And this intersection region is of all constraints is the feasible set. So the goal of work in partial information is to say, how do I construct this feasible set? And how do I operate over this feasible set to perform learning in a meaningful way? Now, it's important to look at the context of this and how statistics could be misused and avoid doing something bad with statistics in the hopes of doing something good in fair machine learning. So it's important to keep in mind that statistics in and of themselves are just descriptions of a population. They're not racist on their own, but they can be used with racist intent. Now, doing something like imputation, where we take an individual and make predictions about them based on their race, or equivalently make predictions about their race based on their attributes, and say, and make hard judgments, is usually going to cause many direct issues and also be extremely inaccurate. However, by working over feasibility, I avoid making any conclusions about an individual and instead make conclusions about populations and reason about this is a labeling that makes sense and this is a labeling that does not seem very likely. So we avoid discriminating directly in a way that we would with imputation. Now, statistics may reflect racial bias in a society, but we're going to use these statistics to understand groups and the biases they face, which we can actually use to help different groups. We're not going to use these statistics to reinforce these biases or make unfounded assumptions about the members of these groups. So to recap, we're trying to learn fairly over multiple groups. We lack annotations in our training data, and we want to use statistical constraints to establish a feasible set of group annotations. These constraints that we're obtaining through statistics will account for our uncertainty over group labels. Each constraint is based on a particular measurement. We get bidirectional inequality constraints to account for statistical error. We have some statistic estimated on our data, and we know it should be greater than some value, but less than some other value with high probabilities. There's a range of feasible values, so we would get 2 inequality constraints out of each statistic. Now, without constraints, any labeling Z would be feasible. And if we had all of the information we wanted in the first place, then we would know exactly what Z star is. In other words, the feasible set Z would contain a single point that is Z star. In practice, we're going to be somewhere between these 2 cases. To generate these statistical constraints, suppose we have a small sample that actually has the fine-grained label information we want. We could do something simple, like estimate the unconditional group frequencies in this sample, the probability that group membership is to group I for each group I, or in other words, estimate demographic statistics. Or we could do something more complicated, like estimate conditional group frequencies. In other words, we estimate the frequency of a race given some observation. For instance, what is the probability that an individual is white given that they obtained a certain level of education? Or given that they were born in a certain country and they immigrated, which is one of the attributes available in the adult data set. We can say something like this, like, what is the probability that an individual is South Asian given that they were born in India? This is very different from saying everyone born in India is South Asian, because that is not true. Instead, we are learning based on the data, the probability that something is true and using that to create a constraint, which we can use to say something in a partial information sense about our overall population. We're going to use these estimated frequencies to then constrain feasible labelings. And this will depend on both the number of labeled examples we have and the number of unlabeled examples we have. We're going to use tail bounds and theoretical data science techniques in order to generate these constraints. And ultimately what we desire is the property that the true labeling is contained in the set of feasible labelings Z. Now, I've only gotten a chance to cover what these statistical constraints are, but we are running low on time. So I will say that given data of this type, we are able to generate these constraints, which gives us a feasible set, which intuitively, the smaller the feasible set is, the closer we are to knowing the fine-grained race information for each example. And the larger it is, the further we are from knowing anything and the closer we are to where we started, where we know nothing. Now, based on this partial information, we're still able to apply modifications of classic machine learning techniques and learn models and get guarantees as to how accurate those models are in terms of their malfare or how well they treat different groups. And we're able to do all of this using only partial information, where the more constraints we have, the better our partial information is, and the more precise the conclusions we make are. I'm going to leave it there, and thank you everyone for coming.
Thank you, Cyrus. It was really, really, really interesting, and for sure a different perspective with respect to how fairness is generally addressed and presented. So thank you a lot for your talk. Are there any questions? I would have actually liked very much to get through the entire talk. I wanted to ask you, Cyrus, just to match what we assume in theory and what actually is feasible to do, not feasible theoretically, but what is actually doable in practice with respect to this idea of having more fine-grained, let's say, subgroups. For instance, in the example you gave about the adult data sets, like in a more experimental setting, would it require for a user to to list down the possible subgroups that we might have, or it's something that is not necessary for?
That's a great question, Christina. I think that the smaller we make our subgroups, the closer we get to individual level fairness. And the topic of this talk was really in group level fairness, because I said, oh, there's groups, and then each group has some performance, and we want to make it so performance is fair across groups. So we can cut our groups into smaller and smaller pieces. But once we get to a certain size, then the probability of ever seeing someone from one of these small groups gets dangerously close to zero. And then we can't make any statistical conclusions about this subgroup. That being said, I'm interested in seeing, is there something between this individual level world and this group level world where maybe we have some fine-grained subgroups, and then there's a level of granularity beyond what we've looked at that we'd like to look at, but we know we don't have the data for. And can we somehow use techniques from individual level fairness within each group to ensure that we're treating even subgroups that we didn't know about at training time fairly as well? Does that answer your question?
Yeah, thank you, Cyrus. Thank you very much.
Of course.
So if there are any other questions, otherwise I think that we can end the session now and resume after lunch. I think that there is lunch available. I don't remember exactly. Where?
Yeah,
I
there is
lost.
lunch here, so I don't know how to. But yeah, we will resume at 1, and there's one more talk about clustering that I hope all of you could attend that, and it will be the last talk. So yeah, thank
So
you.
what should we do here, like for the recording? I don't really know if we have to pause.
If you can pause it now and then continue recording at 1, that would be perfect.
Okay, I just pause it now.